Hello everyone, my name is Andrew Ragooch and I'm from the University of Waterloo, which is just outside of Toronto in Canada. It is with great pleasure that I'm presenting to you this talk today in the very first European Conference on Fracture. The focus of my talk will be on the effect of thermomechanical processing defects on the fatigue and fracture behavior of forged magnesium. I'd like to acknowledge the support of the funding agencies and industrial partners who made this work possible. This particular presentation is detailing the nuances of the structure-property performance relationship of the effect of the processing defects in forged magnesium, but it is part of a larger project where we actually designed, analyzed, optimized, and manufactured automotive suspension components from magnesium for vehicle lightweighting initiatives. So this presentation will aim to summarize a holistic approach we adopted in this research project known as the Integrated Computational Materials Engineering Approach, or ICME, which is an approach to design products, the materials that comprise them, and their associated processing methods via linking material models at multiple length scales. You will see results from this talk spanning the full range of length scales illustrated in this diagram, but in general I'll focus on the micromechanics of the research and then gradually zoom out towards the system level to see how the process structure property performance relationship interacts with the knowledge development at each of these different length scales. As a somewhat of a prelude to this talk, I'd like to present this photo of the final component on the right here, which is produced as a part of this work. Not only because this photo might be visually appealing, but to emphasize the main objective of this work, which was vehicle lightweighting. We targeted a fatigue critical automotive suspension component, and we were able to achieve a 37% mass reduction versus the baseline aluminum component. This type of paradigm shifting improvement was only possible due to the experimental method which was adopted to optimize all facets of the research project. On the right hand side of the slide, you can see a schematic of the forging process where intense pressure between rigid dies forces the material to flow in these internal cavities and conform to the desired component geometry. This can have many beneficial effects for fatigue and some detrimental ones if the process is not carefully controlled, as is done generally at a moderate temperature between 250 degrees Celsius and 450 degrees Celsius. As the component which was selected for this particular investigation had a quite complex geometry, we quickly figured out that we needed a multiple step technique to fully optimize each parameter of the forging process. However, this is a costly undertaking, as die tooling, heating energy requirements, and physical complexity often make the adopted process a compromise of a pragmatic requirement and scientific ideals. We began each forging with a simplistic three-step process, incorporating the bending of the raw billet of the material into this boomerang shape of the component here, then followed by a flattening operation, which was used to redistribute the material to the necessary locations, and then a closed die forging, as shown on the right here, to achieve the near net shape component geometry. Depending on the temperature you choose to forge the component at, the strain history or microstructure memory may be retained or annihilated. In the animations you are seeing at the bottom here of the slide for steps 2 and 3, you can see the evolution of the effective strain being shown within the material for each step, and the fact that the strain of the final stage of step 2 is the initial condition for step 3 is an important thing to distinguish. You can see this more clearly highlighted here in these static images. Once the forged components were actually made, we subjected them to a series of fatigue tests to satisfy the durability requirements which the automotive manufacturer mandated on a fully instrumented load frame with biaxial load actuation. You can see here a video on the left of the physical test being conducted um, with a schematic of the force vectors being subjected to the component shown in the middle here. One of the unique scientific contributions of this particular work is the fact that we utilized in situ digital image correlation, which was a non-contact technique, and it was utilized to detect material defects and incipient cracks in the fatigue critical regions and monitor crack nucleation, propagation, and the final fracture morphology. An important distinction of this is that it's a non-contact technique that does not require any sensing mechanism to be actually affixed to the surface of the component which you want to instrument. Simply all we need to do is paint the surface with a speckle pattern, so you can see that illustrated here, and that was utilized in the critical region of the arm which we knew from finite element analysis, and we provided some margin of safety. So we're looking at a window kind of the surface, and it was observed using a stereo camera system shown on the bottom left here, while the fatigue test was running. So under the peak tensile load reversal, we would capture images. This technique proved to be very successful in understanding the nature of the fatigue failure due to forging defects within the components which were manufactured. As is typical with durability testing of components, a lifetime target was established based on the automotive manufacturer's requirements, which was a combination of various blocks of loading, which were representative of the full life of the component in the vehicle service environment. An example of these two blocks of loading, which were utilized, are shown here, and the videos of the deformations are shown below, as you can see here. Throughout the duration of this project, hundreds of forgings were produced. For the purposes of this presentation, I'll only focus on a subset of them. Here you can see images of 6 of the raw forgings that were collected prior to machining. You can easily see the variation in the geometry of each of these forgings, as certain areas have more or less fill in the various internal cavities of the forging dies. These variations caused by very slight differences in the material flow, alignment of the initial billet within each of the forging processes, and the process control itself, etc., can sometimes result in defects which can be very detrimental to fatigue. Thus, analyzing them and quantifying their effect can be of great importance to develop the forging process to allow for components which will be robust under fatigue loading and be much more predictable in nature. Here you can see the axial strain in the critical region of each of those 6 components during the very first tensile reversal in the fatigue loading. The contour plot highlights in red any regions of the component which exceed 0.4% axial strain. You can clearly observe in certain regions of the forging there is already strain localization indicative of an incipient crack. So on these 2 particular forgings, that's quite obvious. This crack is due to poor fusion in the forging process, which I'll discuss in more detail a little bit later. In general, the strain field is not totally homogeneous, as this is a component level test with varying stress and strain gradients throughout this particular field that's being captured and measured. The slight inhomogeneities illustrating themselves here as red spots surrounded by kind of a yellow matrix or surrounding yellow areas due to the unique microstructure of magnesium and its hexagonal closed packed crystal structure. The local texture in these regions is slightly varying, meaning certain grains may have preferentially strained to accommodate the loading, whereas adjacent grains behave with a higher strength and they have a slightly different texture, which means they will behave with slightly less strain when observed using this digital image correlation technique. Now, if we look at one loading cycle in more detail, we can observe the following. Firstly, the animation on the right, we can see the evolution of the full field strain over the entire cycle. On the left, we can see a green crosshair in the critical region where strain is accumulating at peak tension. And on the graph on the right, we can see the evolution of the strain for that particular point over the duration of the cycle. It begins at 0 load and then 0 strain, and then progresses towards 0.4% strain at the peak tensile part of the loading, and then reverses into the negative strain and compression, and then returns back to 0. Now tracing the exact same information for 5 consecutive cycles, we can appreciate the repeatability of this novel digital image correlation technique for defect detection, as we can trace the same point to have virtually identical hysteresis shown here for 5 consecutive cycles, and then it returns back to 0 as no fatigue crack is nucleated yet. We can see the evolution of the strain versus number of cycles here, and we can see the peaks and valleys are approximately the same for each cycle. Now looking at each of those 5 cycles in more detail, we can freeze frame the images at peak tension for each of those cycles observed, and that we can see that the peak strains that are observed are very similar in each of the 5 cycles, but not completely identical. As the test, we can see 0.389%, 0.324, 0.345%. The reason for this is that it's a component level test with that is load controlled in nature, and we're observing the strain response of the surface due to the applied loading at a much finer scale than the component level. Hence, the variations in each of the strains being observed here, because we're not controlling the strain, we're controlling the applied load. Now, after accumulating 50% of the target life in terms of number of cycles, we can see that the peak strain observed in tension has increased somewhat to 0.6%, indicated by the peak here, illustrating that a crack is now nucleated at the location indicated at the green crosshairs in the image on the left here. We can see that more area is now being enveloped in the hysteresis loop, indicating of more plastic work being done. After 100% of the fatigue block loading, we can easily observe the strain localization indicated here, and we can measure the crack to be approximately 6.5 millimeters in size now. The crack is signified by the region, which is showing 4% strain at the surface as indicated here. So this red line on the image here is what's indicating the crack, surrounded by a field of green here, and that is complementary negative strain to satisfy continuity at the surface. So we are fairly certain that this isn't just some measurement anomaly. We're actually observing a crack here as we have the complementary compressive fields surrounding this tensile saturation of strain here. And we can see much more area being enveloped in the hysteresis loop only in the tensile region, which is what we would expect once the material has cracked. Now increasing to 105% of the fatigue block cycle, the crack has now grown exponentially to 14.3 millimeters in size, and we can see further localization of the strain field in the same region. Finally, the component failed at 129% of the target fatigue life, and this slide summarizes the crack plane which initiated at the location right here at the edge of the forging radius of the particular component indicated here. We don't know yet if it was a forging defect that was that was the cause of the crack initiation at that particular location, but I'll discuss that in a little bit more detail shortly. Now, this is kind of just a brief summary of the nature of the fatigue failure for one of these particular components. But as I had mentioned previously, due to the variations in the forging process and the resulting defects that manifest themselves from those variations, we can look at the other components that kind of get a sense of the variability in the types of failures that we would observe. Now looking at another component in the first cycle, it's largely identical with no indicative signatures of any incipient defects. Moving to 10% of the fatigue life, and still nothing has really changed from the previous example or the previous component. However, now at 50% fatigue life, we can see that the strain localizes at a region indicated by the green crosshairs on the left here, shown at the cursor, which is a totally different location of the component than what we were observing, which was somewhere closer to here in the previous component. After 100% of the fatigue life, the crack, which previously nucleated, had grown larger in that particular location, which is totally different, as I mentioned again. However, when we go to 150% of the fatigue life, we can observe that now there are two cracks, the second of which nucleated at a location which was similar to the previous component. Which one will propagate first to eventually cause the failure of the component is an excellent question that one might ask themselves at this stage. Here we can see that the peak strain at the location of the first crack here is 2.5%. However, if we look at the peak strain in this other location, it's slightly less, around 2%. Moving to the final failure, which occurred at 184% of the target life, we can observe that the final failure was due to the first crack, which was the one that initiated here, and it occurred at a different location from the first forged component, which begs the question as to the microstructural origin. Is that the cause of this disparity in crack nucleation location? So now the benefit of this technique is that we can trace and model the evolution of the peak strain in the critical region of the component as a function of the fatigue life. So the y-axis is the peak strain at the notch, and the x-axis is the number of lives that have been completed, or the fatigue life. And we can do this to understand the amount of strain required to achieve crack nucleation. So we can see that that occurs around here. So that threshold is what's achieving crack nucleation. How it affects the crack propagation rate, which is effectively the slope of this line in the middle regime, and then the nature of the final fracture, which is effectively what peak strain causes final fracture, or what peak strain can be supported prior to final fracture of the 6 forged components which are being highlighted here. Overlaying some of the images of the forging and the crack morphology provides more evidence as to how the strain evolves as fatigue damage is accumulated and then eventual failure occurs at the end of each of these response curves. Comparing the nature of the final failure for the 4 of 6 components, we can observe that 3 of the 4 had similar cracks in the location which was previously discussed. So that's these 3 here. And for the purposes of this presentation, I'll compare and contrast contrast these failures to trace the microstructural origin. Looking at the fracture surface of all of these components, we can observe a similar pattern for the three different failure modes. We can identify the location of the crack initiation to be the location of peak strain, which was accumulated in and highlighted in the DIC images indicated by the green crosshairs in the previous images. Now zooming in on these locations, we can see evidence of a forging defect called a fold line, where external flash fronts fold inwards upon each other to produce a cold weld or a cold shut of material, which results in pore fusion. So we can see that here, and some evidence of it here in these particular images. So now zooming in even further on these pore fusion zones, we can use an optical technique, and we can clearly see some of the faceted morphology of the surfaces in these initiation locations. We also looked at the exact same locations, so we can see the exact same features here using SEM to evaluate the chemical constituents of the material in these localized regions. Under SEM, we observe the area and the matrix away from the initiation site to have a chemistry almost identical to the manufacturer's published chemistry for ZK60, which was the alloy that was being investigated for these particular forgings. When we looked at closer to these faceted regions, we see evidence of a carbon-rich number of particles with poorly fused fold lines surrounding by a carbon-rich zone. So we can see that here. So now carbon is not present in this particular magnesium alloy in detectable quantities. However, we're seeing greater than 30% carbon being shown in some regions here. The source of this carbon is the graphite lubricant, which was used to lubricate the die surfaces during forging to facilitate better material flow and complete die filling. In general, this graphite stays at the surface most of the time. However, this particular region of the forging, which folded inward upon itself, it entrained a high concentration of this graphite subsurface, which resulted in pore fusion. Just to provide some confidence as to kind of the rigor of this technique and the accuracy of this technique, if we go close enough to the edge here, where that we painted the surface to use the digital image correlation technique, we can actually detect titanium dioxide, which is one of the most popular constituents of white pigment in the paint that was being used. So we have very good spatial variation and the capability to detect very small particles using this SEM technique. Looking at the other failures, we could trace large graphite particles to the area surrounding these poorly fused fold lines here, and branching away from these locations, we can see. Now, if we look at the final crack morphology for the three of the components that had this type of failure, we can see that they all look quite similar. However, the starting location and the branching direction is slightly different in the component on the left, as there was a surface defect which caused the initiation to be in that location. If we transpose the crack path from the failure on the left to the two on the right, we can see that there's an offset of approximately 20 millimeters between them. Overlaying the fatigue life prediction from a finite element simulation, we can see that the critical location, which was predicted, agrees well with the two failures that are observed on the right. This indicates that those failures are due to the structural stresses, and that's governing the life of the component, and it's not a forging defect, as the finite element analysis model assumed kind of in a continuous material with no microstructural defects and a homogeneous material property. Now, if we look at the excess material surrounding the forging prior to machining, we can see evidence of two fold edges at the outer perimeter of the material, which originated in this critical region of the arm. Coupling these observations with the forging simulation result, we can also see two fold line edges manifesting themselves in these regions at the tangent points, or at the points tangent to the bending radius of the first forging operation. Now taking one of the full field strain observations and mapping it directly to this location here in the component, we can see that the two locations where the strain localized during fatigue testing can be traced back to these fold lines in the forging. So if we extend these lines from these fatigue cracks, they approximately line up with the fold apeXes that are within the forged component prior to machining, in addition to agreeing well with the forging simulation prediction below. So this provides good evidence of the microstructural origin of these fold line defects and how they manifest themselves in fatigue failure. So some concluding remarks. The microstructural origins of premature fatigue failures were investigated on a variety of forged magnesium components, both at the specimen level and the component level. A novel in situ non-contact approach using digital image correlation technique was used as a screening test to establish the presence of these intrinsic defects and reliably predict their effect on the final fracture behavior in an accelerated manner compared to conventional methods such as strain gauges. The fracture behavior was deterministically traced back to a combination of various effects, all having a microstructural origin, including pore fusion during forging, entrainment of contaminants subsurface, as well as other inhomogeneities in the thermomechanical processing history. And with that, I'd like to thank you for your attention and open the floor for the audience for any questions in this virtual medium. In closing, I'd like to challenge the audience to tell me a concern that they may have as researchers towards using magnesium as a material for fatigue critical components. I'd be happy to answer those questions for you. My contact details are on the references below, and I really appreciate the opportunity to collaborate in such a virtual conference. Thank you very much.